Hi. So in today's video, we will be looking at a concept called water autoionization, and we will be looking at how water will affect our pH calculations. So what is water autoionization? Well, there's a reaction that's always going on, the equilibrium reaction of water, and that's where water will dissociate into a proton and to its hydroxide anion. And both the proton and the hydroxide anion can affect the pH. So water can affect the pH, but usually we ignore water autoionization because the contribution of protons from a strong acid or a weak acid, or the contribution of hydroxides from a strong base or a weak base, is so much more significant than the contribution of protons or hydroxides from water that we don't need to consider water autoionization. But we don't always have to do this. When we work with dilute acid or bases, we have to take water autoionization into consideration. So let's look at our first problem. So our question is, what is the pH of 1 × 10⁻⁸ molar NaOH? Note that this is a dilute strong base. So usually what we do is when we have a strong base, we would simply do the negative log of the concentration to get our pOH and subtract 14 by that to get our pH. So if we do that for this question, the negative log of 1 × 10⁸ is going to be a value of 8. So this will be our pOH. To get our pH, all you have to do is 14 minus our pOH, and we get 14 minus 8 equals 6. So you would say, okay, our final value is 6. But does this make any sense? No, it doesn't make any sense because we're adding a base. So if we're adding a strong base, how is our pH going to decrease and become acidic? This calculation can't work. So what we have to do is we have to take into consideration water autoionization. So let's now move on to how we're supposed to calculate this problem. So the way we're supposed to solve this problem is that we have to take into consideration that water autoionization is occurring. And water is going to break into equal parts H plus and OH minus. Likewise, NaOH, since it's a strong base, is going to break into equal parts sodium and hydroxide. So that means that if H2O breaks into equal parts H plus and OH minus, and NaOH breaks into equal parts sodium and hydroxide, then we know that the concentration of our H plus the concentration of our sodium ions will give us the total concentration of our hydroxides in our solution. So this is a very important equation to know. So let's say we have X amount of H plus. And we know we have 1 × 10⁸ amount of Na plus because that was given in our problem. So we have Na plus equal to 1 × 10⁸ molar. And we then know that from this equation over here, up top, the concentration of OH minus is going to equal 1 × 10⁸ molar plus X. So now what do we do? Well, we know a relationship that can correlate H plus and OH minus. That's our Kw. Kw is equal to the concentration of our protons multiplied by our concentration of our hydroxides. And this will equal 1 × 10⁻⁴. So what is our H plus and OH minus values? Well, we know H plus is going to be X, and our OH minus value is going to be 1 × 10⁻⁻ molar plus X. So we can write our equation as X times 1 × 10⁻⁸ plus X, and we set that equal to our Kw, which is 1 × 10⁻⁴. If we distribute X, we can get 1 × 10⁻⁸x plus X squared is equal to 1 × 10⁻⁴. And we see here is that we can now use a quadratic formula to solve for X. And the reason we're going to solve for x is because x is the concentration of our protons. And if we know our concentration of our protons, we can calculate the pH. So our equation was 1 times 10 to the negative 8th x plus x squared is going to equal 1 times 10 to the negative 14. Let's first rearrange this equation. Play x squared plus 1 times 10 to the negative 8th x minus 1 times 10 to the negative 14 all equal to 0. And let's use the quadratic formula to solve for x. So x will equal negative 1 times 10 to the negative 8th plus or minus the square root of 1 times 10 to the negative 8 squared minus 4a times our c value, all divided by 2 times our a value. And we get a value of 9.5 times 10 to the negative 8th molar, or we also get a value of negative 1.1 times 10 to the negative 8th molar. We don't use a negative concentration, so we can ignore that. And we know our final value of x is 9.5 times 10 to the negative 8th. So if we do the negative log of our x, we should be getting our pH. So the negative log of 9.5 times 10 to the negative 8th will give us a value of 7.02. And this will equal our pH because x was equal to our concentration of our protons. So does this final answer make more sense? Yeah, it makes more sense because now we're adding a strong base, but it's a very dilute strong base, so our pH is going to very slightly increase. So this is how you take into consideration water autoionization when you're doing pH calculations. So when should you consider a strong acid or base is dilute? So when your concentration of your acid or base is greater than 10 to the negative 6 molar, we can consider that as a strong acid or a strong base, and we don't have to consider water autoionization. On the other hand, if the concentration of your acid or base is less than 1 times 10 to the negative 8th molar, our pH is actually going to be equal to 7. That's because the acid or base is too weak to actually affect the pH. But when the concentration of your acid or base is in between 10 to the negative 6 and 10 to the negative 8th, this is where we consider it as dilute. And this region, as you can see here, where it is in between negative 6 and negative 8, is where you have to consider water autoionization. So if you enjoyed this video, make sure to leave a comment, subscribe, drop a like, and I hope you have a good day.